Hello everyone. So in this session, we are going to explore a fascinating concept in artificial intelligence, that is the toy problem. So we have already discussed a lot of toy problems. Now we'll discuss one of the most iconic, that is the tic-tac-toe problem. So by the end of this session, you will understand what a toy problems are, why AI researchers love them. So we can also explore that how a 3 cross 3 grid becomes a rich playground for powerful algorithms like min-max and alpha beta pruning. Okay. So now, before going in and discussing about the exact toy problem, we will understand toy problem is carefully designed, simplified problem. Its purpose is to illustrate a concept or various exercise through different problem solving methods. It is special that it can be described concisely and exactly. There is no ambiguity. We know the rules, we know the exact description, we know the boundaries, we know the goals. Everything is given to us. But as far as when you take about the real world problems, on the other hand, so these are the problems that are actually people are trying to solve or take care more about these kind of problems. Like navigating a traffic, a diagnosis system, scheduling a flight. Because these real time problems involve a lot of uncertainties and ambiguities. The rules are fuzzy and the environment is unpredictable. So, these toy problems be a base for all these real world problems. So, they are applied and tested over the environment and before they are applied to the real world complexity. If you can think of any real world problem that an AI might struggle to define clearly, think about it. Any kind of problem. Now, to just brush up with these characteristics of toy problem, they are not meant to solve real world problems. They are generated for educational and fun purpose. They are typically played on board or paper, so you can easily reason them. The environment is controlled, everything is known in advance. The boundary conditions and the constraints are properly defined. Okay. So this helps us to define or formulate the problem. So once you're formulated with the problem, the algorithm can be applied over it. So they can be converted to easily to computer programs. So based on this, we have discussed a lot of problems. Monkey and banana, missionary and cannibal, eight puzzle, water jug. So many problems we have discussed. Now we will move into the tic-tac-toe problem. That is discussion session of today's toy environment. So this is a more interesting problem where different algorithms like alpha beta pruning, minimax algorithm are applied. So before going in and discussing about the problem in deep, we should understand the basics. Tic-tac-toe problem is a two-player game problem. Players take turns. We will represent it through X and O. Okay, and it is a 3 cross 3 grid problem. Player takes turns. X play first and again O plays. Likewise, they take the turn. The first player to place 3 marks in horizontal or sorry horizontal vertical or diagonal lines wins the game. If all 9 cells get filled with no winner, then it is a draw. So, it's a perfect example of an adversarial search problem. So, we'll be talking about the adversarial search in the coming sessions. So, two opposing agents compete trying to win or at least not to lose. So, every decision is made in the shadow of what the other player might. So, this is a different kind of thinking from other tall problems like finding the shortest path on a map. That's what we were discussing previously. So, when I say a 3 cross 3 grid, how does a 3 cross 3 grid look like? So, it's a simple 3 cross 3 grid, right? You're going to place, if you're going to place like this, x, 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 you're the winner. Like x, 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 winner. You're going to place diagonally, you're the winner. Whomsoever places it. Now, this is a sample board. Already I've drawn it for you. You can see here the x wins for placing it diagonally. Okay. Now let's go through each of the component in this tic-tac-toe problem formulation. So already most of the problems we have talked about state, initial state, goal state, operators. Similarly, a state is any arrangement of X or O's, or it can be even an empty cell on a grid, placing X or O's or in an empty cell. Anything can be your starting state. What is the initial state? Initial state is empty board. All 9, you're going to have the board like this, right? So all your 9 cells are going to be black. This is your initial state. Players, you have already X and O. So they alternate between the moves. Okay. So when we talk about the actions, a player can place their mark in any empty cell. Simple, bounded and well defined. If I'm going to start the game, I can place anywhere. I can place it here. If the O is going to place, it can place it here. Okay. So what is this terminal test? The game ends when one player gets 3 in a row like this. If any X or O gets 3 in a row like this, diagonally or like this. Okay. This utility function is also called as payoff. This is where the AI assigns numerical values to the outcomes. X winning gives a utility of +1. O wins gives -1. A draw means it's 0. These numbers lets the algorithm compare outcomes and make decisions. The 6-component framework, state, initial state, players, actions, terminal state, and utility, is a standard way to formalize any game for AI. So every game problem will be formalized with this. So now we will talk about the state space representation. Okay, that is what is a state space? State space is nothing but set of all possible configurations in that game. Now, each of the 9 cells on the board can be in one of the 3 states. What are the 3 states? You have these board with you. So each of the cell can be in any one of the states, X, O or empty. So the number of combinations is raised to 3 power 9, that is 19,683 combinations. See the combination? But if you observe, most of them are illegal. Okay. For example, what if O has more marks than X? That can't happen because X always goes first. Or what if two players both have three in a row? That's also impossible. All these are invalid states. So after filtering out all the illegal configurations, so we are left only with 5478 reachable states. So that is our true state space. A state is valid if the number of X equals the number of O's. Meaning it's O turn or X has exactly one mark more than O. Meaning it's X turn. And there can be at most one winner on the board. You cannot have more winners. So imagine for a 20,000 possibility, nearly approximately, you have only 5,000 and odd legal moves. So this is crucially called as the constraint satisfaction. Now, out of these valid states, there is exactly one start state, that is your empty board. Okay. So X is about to move and place its turn in any of these 9 cells. So if you talk about the intermediate states as the game progresses, that is 5, 3, 4, 0 intermediate states. There is no winner or not, the board is full at this point of time. So there are 91 terminal states where X wins. Okay. And X has achieved 3 in a row. So the utility value is plus 1. There are 44 terminal states when O wins. So O has 3 in a row. Utility is minus 1. If you observe, O has fewer winning states than X. That's because always X goes first and has a structural advantage. And there are 3 terminal draw states. The board is completely filled with no winner. That is, the utility is 0. If the perfect play happens on both the sides, X or O, then every game ends in a draw state. Interesting, right? That's an interesting point throughout the discussion. Neither player can force a win if it is an optimal move from both sides. Now we'll talk about the depth. If you see the game as a tree, understanding the depth and branching, so it will help us to understand the computational challenge behind it. At depth 0, we have the start state. So you have 9 possible moves because that's the empty state. That nobody has placed anything. If you go to the depth 1, X has marked, it has placed 1 mark on the board. The remaining are the 8 moves. At depth 2, Now O has responded to X, and there are 72 states. When you go to depth 3 through 8, the game progresses. Winners can start appearing as early as from the depth 5. When someone gets their third mark, like it should be in a row. If X places in any of, or O places in any of these, then it's a win. This starts from the depth 5 itself. So at depth 9, the board is full and the game must end. That's the maximum depth. So this tree structure is exactly what a min-max algorithm traverses. It evaluates every possible future game state to find the optimal move. Understanding this is a foundation of what we're going to discuss next. Now, we'll talk about the rules. So every game has their own kind of rules, but formalizing them is essential for an agent or building an agent. First one is board setup. So a 3 cross 3 grid with 9 cells, all initially it is empty. The cells are numbered from 1 to 9, row by row, left to right. The second rule is turn order. X always moves first. Player alternate between the turns. X will play first, then O will play, then X will play, then O will play until the game ends. Rule 3, the legal moves. A player may place only, a player may only place their mark in an empty cell. Important point. Once placed marks are permanent. You cannot change it. No takebacks or no removals. Important point. Fourth one, win condition. A player wins by placing 3 of their marks in a line. Already I have told you, row, column or diagonal. There are 8 winning lines of 2. 8 possible winning lines. What is the rule 5? Draw condition. If all 9 cells are filled and neither player has 3 in a row, then the game is said to be draw. Sometimes called as cat's game. These 5 rules completely define your game. Keeping this clear, the agent can lead to the solution. Now, let's even be more precise. Okay? Cells 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the rows. Columns are 1, 3 columns, 1, 4, 7, 2, 5, 8, and 3, 6, 9. These are represented as columns. 2 diagonals, 1, 5, 9, and the anti-diagonal 3, 5, 7. So these are the possible 8 winning lines. 1, 2, 3, 4, 5, 6, 7, 8. Now, the successor function. This is an AI term for a given state. What are all the legal next states? In tic-tac-toe problem, from any non-terminal state with k empty cells, there are exactly k successors. One for each empty cell where you could place your mark. What is the branching factor? How many choices you have at each step. Start at 9 and can decrease 1 after every move. So the average branching factor across the full tree is about 4. This is what makes a tic-tac-toe so computationally manageable. So even a basic computer can solve it in milliseconds. So these are the key representative states. If you talk about the states, empty boards, cells 1 to 9. X count is 0, O count is 0, cells are empty. Now it is the turn of X. This is our initial state. Okay. Now, X has placed its mark. Count of X is 1. O's count is 0. Empty cells are 9. Now, it's a turn of O. Suppose X has placed the top left corner. Now it's O's progress. O is in progress. Okay. Now, suppose X opens at cell 5 with the center. This is widely considered the strongest first move because it participates in 4 of the 8 winning lines. Okay. A row, column, and both diagonal. It's a middle. Okay. Now, O responds at cell 2. If this is being placed at top left corner, suppose O responds here. Then again, it's a turn of X. Now, X takes the cell 3 after O has responded to cell 2. Okay. Now, O should respond carefully. Okay. X is at 1 and 3. So now, what will the next state be? X is trying to lead and O must always defend. You can see here it's alternatively placed XO, XO, XXO. You see in the ninth state, X has got the winning line XXX. Here X wins. If it is going to be a diagonal row, then also X wins. 1, 5 and 9. Here. Okay. Similarly, here also you can see X wins the center column. 2, 5, 8. If you see, O wins at this point by placing it at 1, 2 and 3. Again, you can see at state 13, O wins via anti-diagonal. Cells 3, 5 and 7. O has 4 marks, 1, 2, 3 and 4, but X has, this is illegal. Supposing if O has 4 and X has 3, that's going to be illegal. But here you can see 1, 2, 3, 4, 1, 2, 3, 4. This is legal over here. But it's a win for O if it has placed an anti-diagonal. Here these two are for draw. This is for draw. No winner or no loser. It's a cat game. So this state is it's at progress. So these are some of the state representation of how X and O places its mark in the board. So when we talk algorithmically, when we talk about the 2 points of algorithm, one is minimax algorithm, another one is the alpha beta pruning. So tic-tac-toe, for teaching the minimax search, it's very classical way of teaching it. So X wants to maximizes the utility score and O tries to minimize it. So maximizing the utility score means X wants to win the game. If O tries to minimize it, then O wants to win the game, which means driving the utility down to -1. So the algorithms look ahead to all possible game outcomes and picks up the move that guarantees the best worst case result. So with perfect play, tic-tac-toe is always a draw. No player can force a win against an optimal opponent. So whomsoever it is a turn, whether it is the max turn or the min turn, they try to max means it tries to maximizes, min means it tries to minimizes. Okay. So with a perfect min-max play, every tic-tac-toe ends in a draw. There is no player can force a win. But if you take this, the alpha beta pruning, the full game tree has 2,55,168 nodes. But alpha beta pruning almost eliminate branches that cannot affect the final decision, reducing it to approximately 2,000 nodes in practice. That's a 99% reduction. So this optimization is a primary reason tic-tac-toe is a perfect teaching vehicle for pruning concepts. Now, to wrap up, we will just see the comparison with the other toy problems. The tic-tac-toe has a valid state of 5,478 states and uses the min-max algorithm, and with perfect play it tries to draw. If you take the missionary and the cannibal problem, it has just 16 states and uses BFS with constraint checking solved in 11 moves. When you take the 8 puzzle problem, it has 1,81,440 states and it uses A star with a heuristic and it tries to find out the optimal path. If you take the water jug problem, it has 20 states and uses the production rules solved in 6 steps. So these are all the fundamentals. Okay. So tic-tac-toe talks about the adversarial reasoning, which is unique to multi-agent competitive environments. So what we have studied here is we have learned about the toy problems and the real world problems, and formally we have defined the tic-tac-toe problem with the framework of state, initial state, actions, terminal state and utilities. So finally we have seen how min-max and alpha beta pruning plays an important role in this tic-tac-toe problem. And also we have talked about the 8 winning lines and the successor function of the tic-tac-toe problem. Thank you. So these are the references as usual. Stuart Russell, Parag Kulkarni and Elaine Rich.